Welcome to this problem walkthrough. In this session, we'll be exploring problem number 1870, minimum speed to arrive on time. This is an exciting problem that tests your ability to optimize solutions by balancing constraints and requirements. Let's dive in. In this problem, we are given a floating point number called hour, which represents the amount of time we have to reach our destination. Along with this, we have an integer array dist that contains the distances for n train rides, where each train ride's distance is given by dist I. These train rides must be taken in sequence, meaning you cannot skip any of them. Now, there's an important condition: for all train rides except the last one, the arrival time has to be rounded up to the nearest whole number, so you must arrive at the next station on an integer hour. However, for the final train ride, this rounding rule does not apply, and you can take the exact time it requires. The goal is to determine the minimum positive integer speed that allows you to complete all the train rides within the given hour. If it is not possible to reach the destination under the given time constraint, we should return -1. The time for any train ride is calculated as time equals distance/speed. The output of the problem is the minimum integer speed required to complete the journey within the given time, or -1 if completing the journey is impossible. Let's look at some examples to understand this better. In the first example, the dist array is 1, 3, 2, and the available time, hour, is 6. If we use a speed of 1 mile per hour, the calculations are as follows. The first train ride takes 1 mile/1 mile per hour equals 1 hour, rounded up to 1 hour. The second train ride takes 3 miles/1 mile per hour equals 3 hours, rounded up to 3 hours. Together, these two rides take 4 hours so far. Now, for the third and final train ride, the distance is 2 miles, and at a speed of 1 mile per hour, this would take exactly 2 hours. Since no rounding is needed for the last ride, the total time comes out to 1 plus 3 plus 2 is equal to 6 hours, which matches the given hour. Therefore, the output for this example is 1, as a speed of 1 mile per hour is sufficient. In the second example, the dist array remains 1, 3, 2, but the available time is now 2.7 hours. At a speed of 3 miles per hour, the calculations change. The first train ride takes 1 mile/3 miles per hour equals 0.33 hours, which is rounded up to 1 hour. The second train ride takes 3 miles/3 miles per hour equals 1 hour, which does not require rounding. The third ride takes 2 miles/3 miles per hour equals 0.67 hours, and again, no rounding is needed for the last ride. This gives us a total time of approximately 1 plus 1 plus 0.67 is equal to 2.67 hours, which fits within the given hour of 2.7. However, if we try a speed of 2 miles per hour instead, the total time exceeds 2.7 hours, so 2 miles per hour is not sufficient. Thus, the minimum speed required for this example is 3. In the third example, we have the same dist array of 1, 3, 2, but the available time is now only 1.9 hours. Here, we find that even at the maximum reasonable speed, it is impossible to complete the journey within the given time. Therefore, the output is -1, indicating that the task cannot be accomplished within the constraints. To summarize, if no positive integer speed can meet the given constraints, we return -1. Now, let's also consider some edge cases. For example, if the dist array contains only one element and hour is very large, the speed required might be minimal, such as dist equals 1 and hour equals 10, where the answer would simply be 1. On the other hand, if the hour is less than the minimum time required for the integer rounding of all train rides except the last one, the task is clearly impossible, and we return -1. Finally, when working with large inputs, such as when n and the distances are at their maximum values, it's important to use an efficient approach, such as binary search, to find the minimum speed quickly and accurately. To begin solving the problem, one straightforward method we can consider is the brute force approach. The intuition here is simple: test every possible speed starting from 1, and for each speed, calculate the total travel time. If the total time is less than or equal to the given hour, that speed becomes a potential candidate. The steps are quite direct. We start with a speed of 1 and calculate the travel time for each segment of the journey. For all segments except the last, the travel time is rounded up to the nearest whole hour, since trains only travel in complete hours. For the last segment, however, we use the exact travel time without rounding. If the total time for a given speed meets the required condition, we return that speed. Otherwise, we increment the speed and repeat the process until we find a solution. While this approach is simple, its major downside is the time complexity, which grows linearly with the maximum speed tested. This makes it inefficient for larger input sizes, especially when the maximum speed is very high. The brute force approach, while intuitive, has significant drawbacks. Specifically, the linear search for the correct speed becomes computationally expensive as the range of speeds increases, making it impractical for large inputs. To address this inefficiency, we can switch to a binary search approach. The key insight here is that the total travel time decreases monotonically as the speed increases. This monotonicity allows us to narrow down the range of possible speeds much more efficiently. The process involves defining a range of speeds, starting with a lower bound of 1 and an upper bound of a sufficiently large number like 10 to the power of 7. We then repeatedly calculate the midpoint of the current range and check whether it meets the travel time constraint. If the travel time is within the allowed hour, we treat this midpoint as a candidate and adjust the upper bound to search for potentially smaller speeds. Otherwise, we adjust the lower bound to look for higher speeds. This approach systematically reduces the search space, making it far more efficient than testing each speed individually. The binary search approach offers significant improvements in complexity compared to brute force. Its time complexity is O, n asterisk log, max underscore speed, where n is the number of segments in the journey, and log, max underscore speed, represents the logarithmic reduction of the search space. Space complexity remains O(1), as no additional memory is required beyond a few variables. One of the strongest advantages of this method is its efficiency, especially for large inputs, as it capitalizes on the monotonic relationship between speed and travel time. A key observation that enables this strategy is the realization that the problem's monotonicity makes it inherently suited for binary search. Additionally, while the largest distance segment can give some insight into setting an upper bound for the search, a conservative maximum speed of 10 to the power of 7 is generally sufficient in practice. This balance of efficiency and practicality makes the binary search approach highly effective for solving the problem. Ultimately, we chose the binary search approach as the ideal strategy for this problem. The brute force method, while simple, is far too slow for larger inputs due to its exhaustive testing of every possible speed. In contrast, binary search leverages the monotonic relationship between speed and travel time to efficiently narrow down the search space, achieving logarithmic reductions in computational effort. This makes it far more scalable and practical, especially for real-world applications. However, there are trade-offs to consider. Proper implementation is critical to handle edge cases, such as very small hour values, large distances, or scenarios where reaching the destination within the given time is impossible. Additionally, the choice of the upper bound for speed must balance correctness with computational efficiency. Despite these considerations, binary search remains the most efficient and robust solution, striking an excellent balance between performance and accuracy for this problem. The problem we're tackling here involves calculating the minimum constant speed required to complete a journey within a given time limit. The journey is divided into multiple segments, each with a specific distance, and we are provided with a floating point value, hour, which represents the maximum time allowed for the entire trip. If it's not possible to complete the journey within the given time, we return -1. To approach this problem, we first consider the brute force method. The intuition behind this method is straightforward. We systematically test every possible speed, starting from 1, and check if the total travel time at that speed satisfies that hour constraint. While this approach is easy to understand, it becomes computationally expensive for larger inputs. To implement this, we initialize the speed variable at 1 and determine the total number of segments, n, from the distance list. Then, we iterate over possible speeds, incrementing from 1 up to a sufficiently large upper bound, which can be calculated based on the maximum distance and the smallest possible segment of travel time. This sets the stage for evaluating whether each speed meets the time constraint. At each speed, we calculate the total travel time for the journey. For the first N1 segments, the train must complete each segment entirely before moving to the next, so we calculate the ceiling of the travel time for these segments. This ensures that any fractional travel time is rounded up, as the train cannot stop midway. For the final segment, however, we simply calculate the exact travel time without applying the ceiling. Once the total travel time is computed for the current speed, we compare it to the given hour. If the total time is less than or equal to hour, the current speed is recorded as a valid solution, and we can immediately stop testing further speeds, returning this speed as the result. If no valid speed is found within the upper bound, we return -1 to indicate that meeting the time constraint is impossible. Critical operations in this approach include the ceiling calculation, which ensures the train adheres to the segment-wise timing requirements, and the summation of times across all segments. This process highlights how the brute force method systematically evaluates each speed while accounting for edge cases where no solution exists. Analyzing the brute force approach reveals its computational limitations. The time complexity is O, max_speed *n, where max_speed represents the upper bound of speeds tested, and n is the number of segments. This makes the approach impractical for large inputs, as the number of iterations grows significantly with max_speed. On the other hand, the space complexity is O(1), as no additional data structures are required beyond a few primitive variables for calculations. To understand this better, consider why we use the ceiling for intermediate segments. The train must reach the end of each segment before proceeding to the next, making it necessary to round up partial travel times. Additionally, the choice of an upper bound for speeds plays a crucial role in determining the efficiency of the brute force method. A poorly chosen upper bound could result in unnecessary computations. These drawbacks highlight the inefficiency of brute force, particularly for larger inputs, which motivates the exploration of optimized techniques like binary search. Using binary search allows us to bypass the need to test every single speed, significantly improving performance. To optimize the solution, we leverage binary search to efficiently find the minimum valid speed. Binary search eliminates the need to test every possible speed sequentially by systematically narrowing the range of potential speeds. Starting with a low value of 1 and an upper bound based on the problem constraints, we calculate the midpoint of the range and check whether the travel time at that speed satisfies that hour constraint. If it does, we adjust the search range to explore lower possible speeds, seeking the minimum. If not, we increase the lower bound to consider higher speeds. This approach drastically reduces the number of computations compared to brute force, as the search space is halved with each iteration. As a result, the time complexity is reduced to O, an *log, max_speed, where n is the number of segments and max_speed is the upper bound for speeds. This optimization not only improves efficiency but also makes the algorithm scalable for larger inputs, providing an elegant solution to the problem. This solution effectively calculates the minimum speed required to complete the journey within the given time using binary search. Here's a detailed explanation. 1. Helper function can_arrive, speed. This function calculates the total travel time at a given speed. For all segments except the last, the time is rounded up using math.ceil, since you can't leave a segment partially completed. For the last segment, the exact time is used since it doesn't require rounding. This ensures the travel time calculation is accurate. 2. Initial feasibility check. Before the binary search begins, we check if it's even possible to complete the journey within the given time. If the number of segments -1, because of rounding effects, exceeds the available hours when floored, it's impossible to meet the time constraint, and we return -1. 3. Binary search setup. We initialize our search range with left set to 1, minimum possible speed, and right set to 10 to the power of 7, a practical upper limit for speed. The result variable is initialized to -1 to store the minimum viable speed. For the binary search loop, in the loop, we calculate the middle speed, mid, and check if it's possible to complete the journey at this speed using can_arrive, mid. If yes, we update result and narrow the search range to potentially find a lower speed. If no, we increase the speed range, left equals mid +1, to explore higher speeds. 5. Return the result. Once the binary search concludes, result will contain the minimum speed required or -1 if no valid speed was found. This approach is efficient due to the logarithmic nature of binary search, making it well suited for scenarios where the search space is large. The time complexity is O, an *log, max_speed, where n is the number of segments and max_speed is the maximum possible speed, 10 to the power of 7. The space complexity is 1, as only a few variables are used. Here, we start by importing the necessary libraries and defining our solution class. The main method, min_speed_on_time, takes two inputs, an array of integers dist representing the distances of each segment of the journey, and a double hour, which represents the maximum time allowed to complete the journey. Inside the method, there's a helper function canArrive, which evaluates whether a given speed is sufficient to reach the destination within the allowed time. It does this by calculating the total travel time. For all segments except the last one, the time is calculated and rounded up using math.ceil, because you can't travel a fractional segment in practice. For the final segment, the exact travel time is used without rounding. The function then returns true if the total time is less than or equal to the given hour. Additionally, we handle an edge case. If the number of segments -1 is greater than or equal to the integer part of hour, it means it's impossible to reach the destination on time, so we immediately return -1. Finally, we initialize variables for binary search, left as 1, right as a very large number representing the upper bound of speed, and result to store the final answer. Now, we use binary search to efficiently find the minimum speed required to complete the journey on time. The loop continues as long as left is less than or equal to right. Inside the loop, we calculate the midpoint mid between left and right. If the canArrive function confirms that the current speed mid allows us to reach on time, we update the result to mid and narrow the search space by reducing right to mid 1. If the current speed is not sufficient, we increase left to mid +1 to explore higher speeds. By the end of the search, the result will hold the minimum speed that satisfies the condition, or it will remain -1 if no such speed exists. Finally, the method returns the result, completing the implementation. To solve this problem, we start with an example where the distances between train segments are given as 1, 3, 2, and the maximum allowed travel time is 2.7 hours. Our goal is to find the minimum speed such that the total travel time does not exceed 2.7 hours. We approach this using binary search, initializing our range with a left bound of 1 and a very high right bound of 10 to the power of 7 to account for all possible speeds, and we set our result variable to -1 as a placeholder. Before proceeding, we confirm that the problem is feasible by checking that the number of segments -1, which is 2, is less than or equal to the floor of the given time, which is also 2.7. Since this condition holds, we can move forward with the binary search iterations. In the first binary search iteration, we calculate the middle speed as the average of the left and right bounds, which is 5 million. To check if this speed is valid, we use the can_arrive function. For the first segment, dividing the distance by the speed gives approximately 0, which rounds up to 1 hour. The same calculation applies to the second segment, also resulting in 1 hour. For the last segment, the exact time is a tiny fraction, approximately 0.000004 hours. Adding these together gives a total travel time of 2 hours, which is within the allowed 2.7 hours. Since this speed is valid, we update our result to 5 million and adjust our right bound to 499.9999. In the next iteration, we have the range again, setting the midpoint to 250.0000. Repeating the calculations, the total travel time remains valid at 2 hours, so we update our result to 250.0000 and continue narrowing the range. After several iterations, we reach the final step of the binary search, where the middle speed is reduced to 3. Testing this speed, the time for the first segment is 1 hour, and for the second segment, it is also 1 hour. For the final segment, dividing 2 by 3 gives approximately 0.6667 hours. Adding these together results in a total travel time of 2.6667 hours, which is still within the allowed 2.7 hours. Since this is valid, we update our result to 3 and reduce our right bound to 2, effectively ending the binary search. The minimum speed required to meet the condition is therefore 3. This concludes the calculation for this example, and the final output is 3. Now, considering a new example where the distances are still 1, 3, 2, but the allowed travel time is reduced to 1.9 hours, we begin with the same initialization steps. However, before starting the binary search, we check the feasibility of the problem. Here, the number of train segments -1 is 2, which is greater than the floor of the allowed time, 1. Since this feasibility condition is not met, it is impossible to complete the journey within the given time, regardless of the speed. Therefore, we immediately return -1 as the result. Moving on to another example with distances 5, 3, 2, 6, and an hour limit of 7.5, we again initialize the binary search range with left at 1, right at 10 to the power of 7, and result at -1. In the first iteration of the binary search for this example, we calculate the midpoint speed as 5 million and check its validity using the can_arrive function. For the first segment, the time is rounded up to 1 hour. The same calculation applies to the second and third segments, each contributing 1 hour. For the fourth segment, dividing 6 by 5 million gives a negligible time, approximately 0.000012 hours. Summing these, the total travel time is 3 hours, which is within the allowed 7.5 hours. Since the speed is valid, we update our result to 5 million and narrow the right bound to 499.9999. After several intermediate iterations, which are skipped for brevity, we arrive at the final iteration where the speed is reduced to 9. At this speed, the times for the segments are rounded up to 1 hour each for the first 3 segments, and approximately 0.6667 hours for the last segment. Adding these gives a total travel time of 3.6667 hours, which is valid. We update the result to 9 and reduce the right bound to 8. At this point, the binary search concludes, and the minimum speed required to meet the travel time constraint is determined to be 9. This value is returned as the final output for the given example. By leveraging binary search, we efficiently narrowed down the possible speeds to identify the smallest one that satisfies the condition. This concludes the process for this example, and the output of 9 is our final answer. To understand the time complexity of our solution, we break it into 2 main components. First, we consider the binary search on speed. The binary search operates over the range of possible speeds, which is from 1 to 10 to the power of 7. With each iteration, the search space is halved, making the number of iterations proportional to the logarithm of this range. This gives us a complexity of O log m, where m represents the maximum possible speed, 10 to the power of 7. Next, we look at the feasibility check for a given speed, which involves iterating through the distance array to compute the total travel time. Since there are n elements in the distance array, this operation takes n time. Combining these, the feasibility check is performed in each iteration of the binary search, leading to an overall time complexity of n log m. Thus, the final time complexity of the solution is n log m, where n is the number of distances and m is the maximum speed, 10 to the power of 7. Now, let's turn to the space complexity. The space complexity of the solution is determined by the space required for variables such as left, right, mid, result, and others. These variables require only a constant amount of space, or O1. Importantly, the solution does not use any additional data structures like arrays or hash maps that scale with the input size. Even the can_arrive function processes the distance array in a single pass without storing intermediate results. As a result, the overall space complexity of this solution is O1. When we compare this optimized approach to a brute force solution, the difference becomes clear. A naive method would involve checking every possible speed from 1 to 10 to the power of 7 and verifying if the total travel time satisfies the condition. For each speed, the algorithm would iterate through the distance array, resulting in a time complexity of m*n, where m is 10 to the power of 7. This brute force approach is vastly inefficient for large values of m. By contrast, the optimized approach reduces the number of speeds tested to O log m by leveraging binary search. This dramatically improves efficiency, especially for large input sizes, bringing the overall time complexity down to n log m. Now let's analyze the best, average, and worst-case scenarios for the optimized solution. In the best case, the target speed is found early during the binary search. For instance, if the required speed is close to the middle of the range, the search might terminate in fewer iterations. However, each iteration still involves a feasibility check, which takes n time, so the overall time complexity remains n log m. On average, the binary search performs log m iterations, with each iteration involving a feasibility check of n. This results in an average case complexity of n log m. In the worst case, the binary search explores the entire range of speeds, performing log m iterations and requiring a full traversal of the distance array in each iteration. Even in this scenario, the time complexity remains O, n asterisk log m. Finally, let's solidify our understanding with a mathematical proof for the big O complexity. The binary search operates over the range from 1 to 10 to the power of 7, having the search space at each step, which results in log m iterations. For each speed, the feasibility check iterates through the distance array, performing a division and sealing operation for each element, which takes O, n, time. Combining these two components, the overall time complexity is O, n asterisk log m. To summarize, the time complexity of the solution is O, n asterisk log m, and the space complexity is O, 1, because no additional data structures are used. Compared to the brute force approach, which has a complexity of O, m asterisk n, the optimized solution is significantly faster, making it well suited for large inputs. When working through this problem, there are a few common mistakes to watch out for. First, failing to account for edge cases with very large values of hour can lead to precision errors. For instance, if hour is a large decimal like 10^6.5, floating point precision might fail during time calculations, leading to incorrect results. Next, avoid using a brute force approach that tests all possible speeds from 1 to the maximum speed limit. This is inefficient, especially for large inputs, such as when n equals 10 to the power of 4, and will likely result in exceeding the time limit. Another common pitfall is mismanaging the calculation for the last segment. Unlike intermediate segments that require rounding up using ceil, the last segment's time is computed as an exact division of distance/speed. Applying rounding here would produce incorrect results. Finally, be cautious with integer division issues. If you use integer division instead of floating point division for distance/speed, it will truncate the result, leading to inaccurate computations and potentially incorrect answers. Now, it's also important to validate the feasibility of the problem up front. If the total distance cannot be covered within the given hour, even at the maximum possible speed, there's no need to proceed with unnecessary computation. In such cases, you can directly return -1. From an interview perspective, there are several key insights to keep in mind. First, this problem is a textbook example of applying binary search. Instead of brute force, you can optimize the solution by searching through the speed range using binary search, which significantly reduces the time complexity to O, n asterisk log, max underscore speed. Additionally, handling intermediate segments with ceil is a common source of subtle bugs, so be sure to implement this logic carefully. Interviewers may also ask you to discuss the trade-offs between binary search and brute force. Highlight how binary search minimizes the number of computations compared to the brute force approach. Lastly, always emphasize the importance of validating feasibility first. If the problem setup itself is unsolvable, you save time by returning early instead of performing unnecessary calculations. To build a deeper understanding, it's helpful to explore related problems that use similar concepts. For example, LeetCode 1011, capacity to ship packages within D days, and LeetCode 875, cocoa eating bananas, both involve minimizing a value using binary search. LeetCode 1482, minimum number of days to make M bouquets, and LeetCode 410, split array largest sum, are also great examples where binary search is used to satisfy minimum conditions or split arrays efficiently. When considering alternative approaches, brute force is the simplest to implement but is computationally expensive, with a time complexity of O, max underscore speed asterisk n. It's only practical for small constraints. In contrast, the binary search approach is optimal, with a complexity of O, n asterisk log, max underscore speed. However, it requires a careful implementation of rounding logic, particularly for intermediate segments. A mathematical approximation might be another option to explore, but it comes with trade-offs. While it can be faster, it risks losing precision, especially when dealing with floating point arithmetic or edge cases, making it less reliable in certain scenarios. Great job following along. To summarize, we tackled the minimum speed to arrive on time problem using binary search for an efficient solution. Keep in mind the importance of balancing constraints with performance. Thanks for watching, and be sure to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!